our senior project is the microfluidicscope. Um, the goal of this project is to increase awareness of the new field of microfluidics. Um, our target audience is K through 12 students who likely have not heard of the field of microfluidics. I know even at a college level, I hadn't heard of microfluidics before I started this project. Um, so our team has collaborated with the STEM Action Center of Utah, which has a mobile STEM program that goes around the state and teaches STEM to different areas in the state of Utah. So this will be our contribution to their mobile program. This project was funded by a National Science Foundation grant, and we had a budget of $2,600, but we were able to accomplish our task with only using about half of that.
Nice. So the goal of our group was to be able to create this low-cost, robust microscope. Like Tom was saying, we were lucky enough to be able to join with the STEM Action Center, and they're going to be able to use it for kids K through 12. So that's where the robustness came in. We figured kids using it, you know, the stronger the better. So we wanted to make this microscope to be able to observe this microfluidic phenomenon, but we also wanted to design a microfluidic chip that would fit on a slide that we could look at through this microscope. And on this chip, we wanted to put a design that was, you know, interesting for kids to see how this fluid interacts on the microscopic level. So also with that, we wanted to put, because everything was kind of on the microscopic level, we wanted to also put a macroscale demonstration right next to the microscope so that these kids could actually directly compare what happens on a macro scale versus a microscale. We could get them excited about, you know, looking at microfluidics and fluid phenomena that way. So David's going to go ahead and talk about a little bit more about the design elements of our project.
Yeah, so as Rowdy kind of alluded to, we wanted to build a microscope, obviously. That had to involve a couple different components. We had to have a optics system that would have a digitally accessible video output, as well as high precision tuning so we can adjust the focus and positioning of the slide within the field of view of the microscope, as well as a frame and housing to hold all of that together. And then we had a couple other separate components. So we needed a syringe pump, which pumps the fluid at a very, very low rate to flow through these tiny micron scale channels. And then the chip, which is basically a fluid channel piece that was attached to a microscope slide that we would be able to image and see how the fluid is moving through that channel. And then the macroscale demo, as Rowdy just alluded to, which would demonstrate the differences between fluid phenomena at the microscale and the macroscale.
So the first piece of the microscope is the optics. The optics are very important because we need to view this phenomena that's happening on the microscale, which is in our thing, it's about the scale of 20 microns. So there were a bunch of different design options that we could have chosen to do, but we ended up wanting to display these phenomena that are occurring on the microfluidic chip directly to a television screen, so many people can view it at once rather than a traditional microscope where you look through eyepieces where only one person would be able to view it at a time. We wanted to add some level of interactivity. So within the optics, you can do that by adding different magnification levels. We wanted to be able to view the chip, the microfluidic chip as a whole, and we also wanted to view it at an increased magnification so we could actually see some of the phenomena happening at a much more detailed level. So we some of the detail that we wanted to see is the non-mixing, and we also wanted to see some droplet generation, which Mo will go into more on the microfluidic chip. So the basic design that had to happen was get the magnification lenses to mate with the actual camera, which will project it onto the television screen. So you can do that by designing an extension tube which will put into focus the image onto the camera sensor. So there were the design process for designing the optics was making that extension tube, and then also having an outer casing that was robust and sleek looking, something that a K through 12 student would want to come up to and interact with. So the next part would be the chip. Oh, and here are some of the results of the optics. The first image on the top left was at about a 4x magnification with a low intensity light, and we found that we got a lot of the some specks and bubbles, and we didn't really like that. And then we tried to increase the illumination power, and we ended up getting a much higher quality image at a higher magnification.
The microfluidic chip, it's a system of fluidic channels, and it's at the micro scale, and at that small of a scale, the fluids will behave differently. So, for example, the flow is always laminar, so you won't achieve mixing. And we wanted to demonstrate that, and so we had two inlets for water to come in, and they will be coming in different colors, and you can see that they don't mix in the image. And we also want to show something a little bit more interesting with droplet generation, and that's just having oil being pumped in at a junction, and that oil cuts through the water and generates droplets. We had some issues with fabrication, so we used the nanofab to fabricate, and it was hard to get access there frequently because we needed to be accompanied by someone who has access, and then we also couldn't get more than one chip printed, unfortunately, because the nanofab also closed down with the university.
Yeah, so the next part of this project was the syringe pump. And in order to move fluid through the microfluidic chip, we needed to have a flow rate that was very, very low. It's about 3 microliters per minute was our minimum flow rate that we were shooting for. And if you want to imagine like a very slow faucet dripping, that's about the flow rate that we're looking for, is like a drip per every 60 seconds. So that with that precision, we needed to have a lead screw and a stepper motor, and then a nice linear stage for to push the syringes as we were trying to get the fluid through the chip. And so there were some design and calculations in that, in determining what kind of step speed we need and what kind of gearbox we need on the motor itself in order to achieve that flow rate. And we were actually able to achieve about 3 microliters per minute, which is the lowest that we thought we would need to go with this chip. We didn't test it very much with the chip, but we have tested it with the most recent version, and the pump was working as good as we expected. So that was great. And then we also have that prototype ready to go and is fully functional at this point. And we actually have some photos of that to show. Eric, if you want to move. Yep, there we go. So as you can see, we have kind of some fun colors in there. Eventually we're going to paint this so it's a little more kind of cohesive as a project, but you can see that we have the syringes sitting in their little holders, and we have a little linear stage that actually pushes the syringes as the pump runs. And inside that box, we actually have the stepper motor, an Arduino controller, and all the other extra wiring that we needed for this project. We also have the NSF logo on the top of the syringe pump just to make the case a little more fun for the kids to look at. We also added some buttons that can start and stop the pump, as well as make it run a little bit faster and a little bit slower, just so the kids have something to interact with. The STEM Action Center was really excited to have something that the kids could actually touch and push, and so these buttons will help let them have something to interact with.
So the next part of the project was the microscope motion and frame for the actual microscope. We needed to make sure that we had very fine adjustment within the actual stage of the microscope so we could get around in the optics and show the entire chip. So what we ended up using is some very fine adjustment screws. We used a 127 thread per inch and a 80 thread per inch. This allowed us to get up and down within the micro scale of the chip very easily. So we can, with this picture in the bottom middle, we wanted to make sure that we had all of the knobs on the same plane, but we had to implement a bevel gear in order to do that. This also allowed us to, as you can see on the picture to the right of the little bevel gear, we have the little stack of the X, Y, and the Z components. So this gave us good range. We can go about 10 millimeters in every direction with a very, very fine adjustment, which allows us to get within the optics and see everything we need to see. The actual frame of the microscope was built using a big C-bar, aluminum C-bar, with a foot built out of 80/20, which was donated to us. This gives it a very sturdy but slightly heavy design. But when we're dealing with a bunch of children who are going to be pushing this thing around, we wanted to make sure it was very compact but also strong. So we have some pictures of the design built on the next slide, which David is going to go into.
So starting on the left, you can see the final result of our fine adjustment stage. So those two knobs will adjust the position of the slide left, right, and forward and backward, so that the portion of the slide that you're looking for gets exactly in there. And then below that, in that white 3D printed piece, is the vertical actuator. So that silver knob will allow the slide to go up and down, so that the slide is in focus with respect to the optics package. In the middle picture, you can see that bevel gear system with the high precision screw attached. That allows us so that both of our knobs are roughly in the same spot on the same side, as opposed to in front of the microscope. And then on the right side of the screen, you can see our fully built microscope at the bottom with that 80/20 frame, the aluminum, and then the full optics package in black at the top. One thing we weren't quite able to get done, given the time constraints and some of the issues with the pandemic going around, is we weren't able to finish. We wanted a case that would cover that 80/20, that black portion at the bottom. But we're in the design for that, and we hope to have that finished before we send it off to the STEM Action Center. But unfortunately, that's not available for us to show today.
Nice. So onto the macro scale demonstration. So what we decided to do with that is everything we've had so far is on the micro scale. And so we wanted, because we were using school-age kids, we wanted something that was something that they could visually look at and kind of put their hands on and play with and break if they needed to, rather than the microscope. So we went ahead and put together this macro scale demonstration by bending some plexiglass and forming this tank with a channel in it. In that channel, we were able to put a cross-section of an airfoil and be able to run this liquid past the airfoil and see how the fluid interacted with this object in the channel. We also were tipped off on some information that adding mica to the fluid would provide a lot better visual effects. So we went ahead and added some mica crystals to it. And it turned out really cool. You can see exactly how the fluid interacts with the macro scale demonstration. Here is the fully built demonstration. You can see in the upper left-hand corner, we also integrated a light strip in there that the kids can turn on and off. And what that light was doing was actually bouncing off all of the crystals in that mica and it created some really cool effects that you could see when the pump was actually running the fluid through the tank. In the next slide, we've got a little video to kind of see. You can see how it kind of interacts with that airfoil channel. Hopefully that'll go ahead and work, but you're really able to see how that fluid comes together and interacts with that airfoil. We were able to adjust the airfoil. You could see kind of the turbulent flows and little back eddies that showed up, and how you could manipulate those. So kind of fun. Hopefully it will get the kids excited about it. I know I was super excited about it. Our group can attest to that. I was super excited. But overall, this project this year, you know, we had a lot of stepping stones that we jumped through, hurdles we had to jump through. As all of you know, every group had the problem with this pandemic, but we were able to get over with it. We're pleased with the success that we had. We're looking forward to the future, to be able to work with the STEM Action Bus and be able to get our project on the bus and get it around, like Tom was saying, through the whole state and get kids excited about it. So we're really excited about moving forward, and hopefully, you know, things will get better as an economy and society. We can really get this project out there to young engineers. So if anybody's got any questions or anything, we'd be happy to go ahead and go over anything like that.